So today we want to talk about how we can solve the eigenvalue problem. And if you recall from our last lecture, we know that if I had an operator omega and an vector, let's say v, and when omega acted on v, the v would just get rescaled. And this rescaling factor was denoted with small omega, and they were called respectively, that is, the capital omega was called the operator, the ket was called the eigenket or the eigenvector, and the omega was called the eigenvalue. And today we will see how we can determine these v's and omegas, that is how we can determine eigenvalue and eigenvector. So let's get started. Note that while writing the eigenvalue equation omega v, we wrote it as small omega v, right? But we mentioned that there is an identity operator over here implicitly. So the first thing we're going to do is that we're going to make that explicit. So let's write the identity operator like this. This is a 1. And also note that we are considering a finite dimensional vector space. So omega will just be a matrix. And yeah. So from here you can write omega v is equals to small omega, the identity matrix, and v. And you can just pull all the things from here to here. That means you can write this line. There are two ways you can do it, or two ways to justify this thing. In fact, the only way to do it is to just add minus omega identity v on both sides, because in vector space there is this additive inverse as well. So that's how it's well defined, and you can add it on both sides. And on the right hand side there will be a 0 vector. So then what you can do is that you can factor out this get v, and yeah, so let's call this thing as m. That is a matrix omega minus an identity matrix, and there is a scalar with small omega, and let's call this whole matrix as m. So ultimately what you will have here is something like this. You will have m, you will have a v, and on the right side you will have a 0 vector. So assuming m inverse exists, we can do the following. That is, we want to solve for these v's first. So this will just be m inverse acting on the null vector or the 0 vector. Now the problem is, that is the problem with this equation, is that let's call it equation 1. So this vector v over here, it is a non-zero vector in general, non-zero, and the matrix elements in this m inverse one are also non-zero, but this is a 0 vector. So think of it like this, that the 0 vector has all the elements or all the components as 0, and what you're doing is that you are acting with some m inverse that has non-zero elements, and it is turning that 0 vector into something non-zero. So that doesn't make any sense, because how can you can get something that is this v over here is something out of this nothing, that is this 0 vector with some non-zero operation. So let me write it down formally. So equation 1 means that we are getting something that is my ket v, that is something non-zero out of nothing. That is a zero vector, and this doesn't make sense. So we must have done something wrong, and the thing that we have done wrong lies over here, is assuming M inverse exists. This assumption is wrong. Because we assumed it, and we are getting something that is self-contradictory. So that's why we are saying that our algebra was correct, our calculation was right, but whatever we started with was wrong. And this is the axiom that we started with, right? Especially when we went from mv to 0, that is, we were trying to solve for v. So recall that. So okay, let me just write this point down. So M inverse doesn't exist because we assumed M inverse existed, and if we do that, we get something out of nothing. So we are saying M inverse doesn't exist. So now we want to recall from our experiences with matrices, since we are dealing with a finite dimensional case. Inverse of this matrix was given by the transpose of the adjoint of M divided by the determinant of M. And the only way M inverse will fail to exist will correspond to determinant of M. Let me just write it in a bold mark so that I can emphasize it better. Determinant of M is 0. So this is the condition that we are after, because we started with assuming that the inverse of M exists, but later we found out this is not the deal, this is not the correct way. So we are saying that it's the inverse of this M either exists or it does not exist. So we finally concluded with this point that M inverse doesn't exist, and this M inverse doesn't exist will correspond to the determinant of M to be 0, because when this goes to 0, this M inverse fails to exist, or it blows up, and whenever something blows up, we don't know what happens, and hence we say it doesn't exist. So how does that help us? That is this condition over here. Let's call it equation 2. So let's now recall that we wrote M as omega minus small omega times the identity, right? This is how we wrote it. So let's just put that over here. Determinant of capital Omega, small omega, identity matrix. This is equals to 0. So this equation will play a key role in finding the eigenvalues, that is the omegas. So let me just write this down. This will play a key role in finding the eigenvalues of an operator. And what we can do right now is that we can also recall the first thing that we did, and that was just that is this guy over here. this whole thing, and what we want to do, we can project it into a basis, and the reason will be evident very soon. So this will be this guy, right? And what we're going to do now is that we're going to dot both sides with some basis vector I, because we want to project it. And remember, projection is equivalent to taking inner products. So let's do this and take some projection in the I basis, and this is just 0, the number 0, not the vector 0. So this is just 0. So the whole idea of this dotting with I, that is taking a projection, is to convert it into a number, something we can solve easily. And now what I'm going to do, I'm going to introduce the completeness relation. So let me just write it down over here in a very small manner, that here the completeness relation was injected. Let me show you how. Because I want to get components, I injected the identity the completeness relation in this manner, that is over here. Let me go to another color so that you can see better. Because remember, if your j's are basis, then this is just the identity operation. Okay, and this will be just equals to 0. Oops, let me switch to black color again. And now what you have is that instead of having an equation with matrix, now you have these components. So again, you can use the linearity of Bryan-Kett, and this will be I omega. Okay, let me put a bracket over here. There will be one j over here. This omega is a scalar, so bring it out, and this will be I. The identity is over here, so and identity times j is just j itself. And finally, recall that j p, that is this guy over here, is just vj. That is the component, the vj component, or the component corresponding to the j basis itself. So this is vj, and finally you have 0, right? And now this is a matrix element, right? Recall from your lectures from the previous week that this will correspond to, if omega is a matrix, this will correspond to omega ijth element, and this small omega is your eigenvalue, it's a number, and this ij, since they are basis vector, this is just delta ij, and what you have is vj equals to 0. And this whole thing is something that is when you set the determinant to be 0, this will give you the characteristic equation. And so this is another important part. So let's call it our equation 3. So if you take 3 and then set the determinant to be 0, you get the characteristic equation. And this is given by the following. Oops, sorry, I shouldn't have used j because that is a bit confusing. So let me use another index. The characteristic equation will be given by where m is the dummy index and n is the number of the dimensions that we're dealing with, that is the dimension of the vector space, and this will be equals to 0. So you can think of this as a polynomial expansion, and this equation is our characteristic equation. And the polynomial that is because look at this, this is an expansion in the form of C0 omega 0, C1 omega 1, C2 omega 2, and so on up to Cn omega n, right? And this is equals to 0. So this is a polynomial over here. And this is called the characteristic polynomial. So with all these tools, especially this one, equation 2, we will try to find the eigenvalues of a specific matrix operator, and after getting the eigenvalues, what we can do is that we can use this eigenvalues to get our eigenvectors B, that is these guys, and this equation will help us in doing that. And in the next video we will see examples of how we can find the eigenvalues and eigenvectors of an operator. Thank you.